So let's look at heterocyclic compounds. Can they be aromatic? Yes, they can. So some simple definitions. A heteroatom is any atom that is not carbon or hydrogen. So you might recall that from organic 1. A heterocycle is a cyclic compound with at least one ring atom that is not carbon. Here's a great, these examples are examples of heterocycles or heterocyclic compounds. You see here that one of the ring atoms is nitrogen, oxygen, and also nitrogen. Could be sulfur, could be phosphorus, etc. And here are the common atoms that are part of the heterocyclic compounds. These are the heteroatoms: nitrogen, oxygen, sulfur, phosphorus, aluminum, or silicon. Not so much on aluminum and silicon and even phosphorus, but I would say nitrogen, oxygen, sulfur are the most common ones. So let's begin. How do we know if a heterocyclic compound is aromatic or not? Well, we still follow the same rules, the criteria, and let's begin. But of course, I'm going to add some more information here for you to consider. So let's begin. If we were to say, are these cyclic compounds? Then the answer would be yes, they're cyclic. Cyclic. And cyclic. Two. Do we have a p orbital on every atom in the ring? Well, if you look at nitrogen here, it has a lone pair on it. So if you do the hybridization, this would be an sp2. So it must have a p orbital, an empty p orbital on it. And there are p orbitals on the other carbons because we have those pi bonds. So yes, we have p orbitals. What about here? Well, let's actually put the lone pairs on oxygen. Recall that to complete the octet, oxygen needs 8, and that would be 2 lone pairs. So let me just clean them up. I like to just draw them neatly if I will succeed, but let's start. So here we go. Not bad. So yes, the answer is yes. Why? Because there's resonance in this. And if all you have to do is move those lone pairs, and then these pi electrons in the pi bond would move up and they would make this structure. There's a positive charge on oxygen. That's the formal charge. And then there's a lone pair on there. And this is the structure. So if you were to determine if this is sp2 hybridized, you would see that there are 3 domains. So yes, this is sp2 hybridized. So there must be a p orbital, an unhybridized p orbital. Remember, if the one way of knowing that you have no p orbitals is if you have an sp3, it means you used up all 3 p orbitals. Remember, there are 3 p orbitals. So yes, it has a p orbital, an overlap. Let me use the same color. And the same thing would apply to pyrrole. And pyrrole would also, again, move those lone pairs just like the previous example. And you would get also a positive charge. So that would be right there. So once again, this is also sp2 hybridized. So again, the rule is if you have sp2 hybridized, then you have a p orbital on every on that atom, and therefore you have a p overlap. Third, are they planar? And yes, they're six-membered rings or less, so they should be planar. And then four, which we will need the help of the representations below, is how many pi electrons are there in each system. And the way to look at that is to, of course, use some help from the representations below. So if we look at pyridine, we have 6 pi electrons. So there's 2 in each, 2, 2, and then 2. So that's a total of 6 pi electrons. Now you might be saying, okay, well, what about this lone pair? Wouldn't that be part because it's an sp2? Well, let's look down here. So this would be pyridine, and this would be the overlap if it's sp2 hybridized. So this is sp2. So if you notice here, this lone pair does not contribute to aromaticity. And why is that? It's because it is not parallel. It is not in that p orbital. It's in an sp2 orbital, and it's perpendicular to the p orbitals. And remember, aromatic, the criteria for Huckel's rule is to have those electrons in parallel p orbitals. So you can have a continuous overlap. And of course, those electrons would be in that overlap. So you can't have electrons outside of that overlap count toward the overlap. It makes no sense. So then those do not count. So you do not count. This lone pair does not count. So therefore, we only have 6, which means it satisfies 4n plus 2 pi electrons. So that means this is an aromatic compound. Now let's look at furan. So we drew this structure, and here's a nice representation of furan. So furan rehybridizes like that, and it becomes an sp2. And if you notice, only one of the lone pairs contributes to aromaticity. Only one, not both. So this one right here, like I said, does not contribute to, let's say, delocalized electrons in ring. Let me just clean this up a little bit. So you only count one of these lone pairs. So therefore, we have only one. Here's one lone pair. So that's 2 electrons, 2 pi electrons. You can pick either one, but you only pick one. That's 2. And that's 2. So therefore, this now also has 6 pi electrons. And again, that would be aromatic as well. Pyrrole also follows same logic here, is that we have, if we look down here, if we rehybridize it, because of resonance, it can become sp2. And notice where this lone pair right here is. It's in the what? It's in the unhybridized p orbital. So it does contribute to the delocalized electrons in the ring. So therefore, we also count them. We count this lone pair. And then we have 2 there. And 2 there as well. So that would be 6 electrons. So that is also aromatic. Now, what can we remember as a kind of like shortcuts from this? And by the way, do not diminish the importance of this. After all, you have purine rings, and those are in DNA. So your DNA molecules have, your DNA molecule has, its foundation is really purine rings. Those are the adenine, guanine, etc. And purine rings have nitrogen in them, and they are aromatic. So there you go. Aromaticity is important in terms of DNA as well. So do not diminish the importance of this. This is not just organic chemistry outside of biochemistry. You'll also learn when we are in class about how benzene actually benzene is very toxic and it can lead to cancer. So let's look at ways of kind of like looking at a shortcut. So here's how. Let's look at nitrogen and phosphorus, since they are in the same period, in the same group. So you have nitrogen, phosphorus, and then arsenic, but we're only going to look at nitrogen and phosphorus. We're also going to look at sulfur, oxygen, and sulfur. Okay, we'll just going to, let me delete this here. Oops, I deleted the whole thing. That's all right. Okay, so for nitrogen and phosphorus, what you need to do is the following, is remember, if you have a double bond, if there is a double bond, then do not count lone pair. Toward aromaticity. I'm just going to write toward aromaticity. So if you go back to pyridine, notice how we have a double bond here. If it just looks at that before you even do a resonance structure, do not count that lone pair. But if you have single bonds only, then you count the lone pair. That's a nice shortcut. For oxygen and sulfur, only count one lone pair. Only one lone pair. If there are two lone pairs. So if you notice here, we only counted one of them. We didn't count both of them. Okay. So the moment you have less than two, then you do not count anything at all. So again, we only had one lone pair or two lone pairs here, so we counted only one of them. So going back to the nitrogen, notice how there's a double bond here. So I didn't count this lone pair, but here there are single bonds, so I counted this lone pair. It's a shortcut. Of course, this is not like a rule that is set in stone, but it should work for our class. When you come back, we're going to learn about acids and bases in terms of aromaticity.